So here's a video for you. First one. It's called types of numbers. As you can see on the screen, there are all different ways that we represent numbers that we're familiar with that we can look at. We've got the numbers 3 through 8 represented in a variety of ways, even with little doggies. So let's start with numbers that you know about. I think that you're familiar with counting numbers. So counting numbers, those are the first numbers that you actually ever were accustomed to, probably before you even started counting. You might have just looked at things. Probably the first number you actually counted was 2. You never really count 1 because it's just 1. But when you start with, 2 of this, 2 of these, 2, 2 ice creams and things like that. But counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, those are numbers that you count with. As you got a little older, you were introduced to whole numbers. Whole numbers are the counting numbers, but the only extra little piece now is that we've got 0. Covers all the whole numbers. So contained within the whole numbers are the counting numbers. Another type of number. Next came the integers. The integers are your positive and negative whole numbers. So the integers include all your whole numbers, 0, 1, 2, 3, 4, 5, 6, whatever, which includes your counting numbers. But now we go the other directions. We've got from negative whatever, negative 3, negative 2, 1. So it's your positive and negative whole numbers. Those are what integers are. So that's kind of a mathy word that you'll see from time to time in problems. We've covered all of the, the nice numbers that are really good and delightful. The next layer on that are what are called rational numbers. Rational numbers cover most of the rest of the numbers that you're used to seeing. Cover your fractions, your decimals. I've got -5 in there, which -5 we know is actually down here in the integer category. 2.7 repeating, so 2.7777777 whatever repeating. That's a rational number. Rational number is, let's see, technical definition, any number that can be expressed as a over b. So if we can turn it into a fraction, we can make it, we can call it a rational number. So 1/4 obviously is a fraction. 3.7, that's 3 7/10, which is the same as 37/10. 2.7 repeating. We can go into the details of how to turn that into a fraction. Trust me, but if you want to see that tomorrow, we can go into how do you turn a repeating decimal into a fraction. Okay. The other one is rational numbers can be placed exactly on a number line. So there is a precise location for every rational number. I could put -5 on a number line. If I had a number line, which maybe I can grab one now, I don't have one right handy. But if I had a number line, I can find where -5 is. I can find where 3.7 is. I can find where 1/4 is. I can put it precisely there. I could even put 2.777777777 someplace exactly on a number line. So that's a more like operational definition. Here's the formal one. We can turn it into a fraction. Operationally, if I can put it exactly on a number line, it's a rational number. So if we've got rational numbers, I don't know if it directly follows, but there are these other things that are called irrational numbers. Okay, irrational numbers, you've heard of pi. Pi is irrational. Pi goes on and on forever and ever. It doesn't repeat. 3.1415926, and others of you, I'm sure, know more decimal numbers than I do. There's this another number called e, which is 2.71828, and then it keeps going on and on forever, and it doesn't repeat itself. And it's got some math applications. The square root of 17, it's irrational. When you put your button on the calculator, the square root of 17 button, when you push that button, it gives you like a 10 decimals out, but it never really ends, never repeats. The cube root of 13, numbers like this, 1.2122122212221. So there's no pattern, there's no repeating piece. Looks like every time we add another 2 in there, and then we go to a 1. So those are irrational numbers. I can't put them exactly on a number line. I can approximate pi. I can put, I can find 3.14. I can find 3.1415. I can find 3.1415926. But I can't find pi because pi keeps going on forever and ever and ever, and there's no repeatability in it. Okay, so that's the difference between a rational number in my world and an irrational number. Is I can put a rational number on the line. I can't put an irrational number on the line. Okay? So when we take the set of rational numbers and irrational numbers and put them together, they make up real numbers. So my real numbers are all my rational numbers and all my irrational numbers. And it may look like there's some things that fall that are real numbers that are outside of this, just the graphic. So, this space really means nothing out here. Real numbers is all of the rational numbers and all of the irrational numbers. Maybe I should have made two rectangles. I don't know. But your numbers are either rational or irrational if they're real numbers. They don't mix together. We can't have a rational, irrational number or something like that. Okay? So if we have real numbers, it might follow that we have numbers that aren't real. We have what are called imaginary numbers. Okay? And imaginary numbers are really no more imaginary than the number 3. Somebody made up the number 3 long, long time ago. Somebody decided that, anytime we see, I don't know, let's see if I can make something really quick. Okay, 1, 2, they're supposed to look alike. Okay, that represents 3, so they said, oh, okay, so anytime we have that many of something, it's 3, and then they came up with the word 3, but it's just made up by somebody. So imaginary numbers, somebody made up. And imaginary numbers help us to find out things like the square root of -9. Okay, square root means what do you multiply by itself to get the answer. So there's nothing I can multiply by itself and get a negative answer. I try -3. -3 times -3 is 9. Okay, that's not the same. I can't do 3 times 3, so I typically can't multiply a number by itself and get a negative number. And I can't do one of each to do that because then it eliminates the square root thing. So what someone did was they said, okay, here's what we're going to do. I'm going to invent a number. I'm going to invent the number I. And I'm going to say I is equal to the square root of -1. Okay, fine. So that makes I squared equal to -1. If I square this side, I squared means I multiplied by itself becomes I squared. When I square something under a square root, I just get the thing. Okay? So I squared is -1. That allows me then, go down here with this, to rewrite this as 9 times -1. And then I can rewrite that as 9 times I squared. Okay? And then I can take the square roots of both pieces. I can take the square root of 9, and I can take the square root of I squared. The square root of 9 is 3. The square root of I squared is I. And so the square root of -9 is 3i. And that's just what it is. So when we see the imaginary number, we see things with i's hanging around. It is useful in electronics. It's useful in fractals and other things like that. It's got a lot of actual, some kind of cool math applications, some cool technical applications in AC current, but it's just another type of number. Okay, it covers the real numbers, and the reason they call them imaginary as well, they're not real, so we've got to give them some name to contrast with that. Just a really brief introduction. Don't get too stressed out about it, other than knowing that imaginary numbers exist. Something imaginary exists. So when we take a blend of my real numbers and my imaginary numbers, I can have that. Those are called complex numbers. So complex number, got a real part, got an imaginary part. 3 plus 5i. It's a complex number. Yeah, we can make a bunch of them. I mean, I can do 3.7 minus 2i. I guess I could use the square root of 17 plus 4i, something like that. I've got a real part, I've got an imaginary part. That's what makes it complex. Okay, I guess when you start combining real and imaginary, it does get sort of complex in life also. And that's about all there is on that one. So we've got a variety of numbers. This would probably be the graphic that you're going to want to try to get down. This sort of thing in some form or another. You might find a better representation someplace on the internet. That's fine, but some way to get at What are the types of numbers? How did we start back here with counting numbers that you've known since you first counted two of something, 2 cookies or whatever, into the whole numbers, the integers, the rational numbers. Then we've got the irrational numbers. Those make up all my reals. And then I got my imaginary branch, and the combination of those two is my complex numbers. How all the numbers fit together, how they build from one thing to the other. That's really what we want you to understand as we go. Okay? So, make note of this. Pause if you need to get it down. I've been yammering for a few minutes. So, thanks for listening. Thanks for watching. Hope you learned something. If you have questions, of course, that's what tomorrow is for. See you then.